Okay, so again, good evening to all of you. Thanks for coming. Um, so today is going to be the 11th lecture, uh, and see, fourth. And for some reason, uh, whenever in the past I have, whenever the years have changed, I've had this habit of when I'm writing my dates of remaining stuck in the previous year. So, for example, I would find myself writing January 4th, 2020, right? But this year, for some reason, I don't know, I feel happy writing 2021. Like it just seems like an auspicious year. We'll see. Of course, I don't know. Maybe that's not a very scientific statement to make. But okay, so last time we talked about the area operator and its application to black hole entropy. So today, what I intend to do is I go into more detail into this calculation of black hole entropy. And so there will be a couple of things I'll be talking about. One will be the action in the presence of boundaries. And when you have a inner boundary or an outer boundary, and what happens is that the presence of a boundary, certain special kinds of boundaries, black hole horizons or isolated horizons, you get a Chern-Simons theory living on the boundary. This gives us a constraint on the, so there's a certain constraint on the surface states, and then you can do basically the state counting by just calculating, determining the Hilbert space of the Chern-Simons theory with punctures. So you calculate, do the state counting. Which is equal to basically the dimension of the Hilbert space. Let's see. Okay. And now, before that, I want to actually go back to a couple of lectures and confess that I have made some mistakes, which I don't know whether I think I mean, if you're feeling kind, they might be forgivable, but I feel very ashamed to have made such mistakes. So let me tell you what they are, and you can decide. One mistake I made was in the definition of the Kodama state. Now you might remember that I defined this Kodama state as this exponential minus some coupling constant k by 2 pi or something like this, and then I here over your 3 manifold. And then I said that you have the Hamiltonian constraint. So the Hamiltonian constraint looks like this. You have E A I E B J F A B K and then epsilon I J K. And I said, well, this solves this Hamiltonian constraint, and I was wrong. Okay, so I truly sorry about that, because I had forgotten one very important aspect, that it solves the Hamiltonian constraint in the presence of a cosmological term. Okay. So during that lecture, I had somehow managed to convince you all that when you take the differential of this state with respect to the connection twice, you get 0. And nobody had corrected me on that account. But I felt that there was something wrong with what I'd said. And today I'll correct that. So when you have a cosmological term, what happens is that your Hamiltonian has this expression, has this part, but then it also has another part, right, which comes from the lambda. And this part has the same structure, ij k epsilon a b c epsilon ij k, like this. So this is the extra part that causes the due to which the Kodama state is a solution. And the way it works is, so if you look at this expression now, you have epsilon ijk, and then I can take 2 copies of my triad and 1 copy of my epsilon factor common, and I get FABK minus lambda by 3 epsilon ABC EA, right, and then I get EA EC ECK. So I'll put this K here, right? And this is the expression which solves the this. So when I act on this psi k with this expression, what I do is I make this the momentum operator, right? So it becomes a derivation with respect to but I only need 1 of these factors. So the other 2 factors, I can leave them as they are. And so this becomes some IH bar del by del ACK. And this will solve this will annihilate the Kodama state because as I showed, when you take the derivative of this state with respect to the connection, right? You basically get a copy of the curvature, the field strength tensor, right? So when you do this, you get whatever is over here, k by 2 pi, and then you get f abk epsilon abc, like this. So when you put this back in here, the epsilon will cancel out, right? And you'll have this extra factor of ABC, right? So that also I should put here ABC. So this ABC and this one, they will contract. You'll get some delta functions. You'll be left with another copy of F, which will cancel out this copy. So here, what happens is that there is a relationship between the Chern-Simons level, right? This K is called the Chern-Simons level K, right? And lambda, and cosmological constant lambda. And this has a very interesting implication, which is that in the quantum theory, so this Chern-Simons action is gauge invariant, right? But if you consider the quantum theory, so how do you know there are no other solutions to the Hamiltonian constraint? No, no, I'm not saying that there are no other solutions. I'm saying that this is one solution. So, right? I mean, I'm not sure what what the point was, but I mean, I'm just saying that this is a solution. So, but in the quantum theory, what we would do is okay. So we would for instance, write down the partition functional, right? Point was that all no. Do you mean the point being like something that I said in my in that lecture, that all solutions should be considered? I'm not sure I follow, sir. Can you tell me? Can you elaborate? Saida sir is saying, pointing out something that point was that all solutions should be considered. Sir, I don't follow. So I would be appreciated if you can elaborate on what you're saying. Okay. Thank you, sir. Right. So, okay. No, not only in the quantum theory. So this is gauge invariant with respect to this thing, small gauge transformation. Yes. So Dev-Malya, that's exactly what I'm going to talk about, right? Small gauge transformations. And if you consider under large gauge transformations, those which are disconnected from the identity, right? So under large gauge transformations, what happens is that this S undergoes a shift by a constant amount. There's some constant, and when you because of this shift, what will happen is that, let's say you write down this state. Let's say you write down this exponential. So under a large gauge transformation, this will pick up an extra phase, right? So so if you want the state to be invariant under this shift, what this implies, so this is some constant which is some function of k. It's just some k times something else. So this implies that k has to be quantized. K becomes some nk naught. So this will also imply that lambda is quantized. By virtue of the fact that this state is a solution of the Hamiltonian constraint for a space-time with a cosmological constant. Now, Dev-Malya is pointing out that there are issues with the normalization of the Chern-Simons term and so on and so forth, and that, like I had mentioned, these issues have prevented people from properly using this expression as a and treating that as a proper theory of quantum gravity. So, but it is a bona fide solution constraints, and I think that is worthy of mentioning. Okay, and the other mistake that I had made, the second one, is that when I've been talking about the Gauss constraint, I talked about I think what I had done was I was writing the gauge covariant derivative, and I believe I said it's of this form. So there is some Christoffel term, and then there is a gauge connection here, and so this acts on the internal indices, and this will act on the space-time indices. And so I had said that the Gauss constraint can be written in this form, but as my student Devadarshini pointed out, this is also incorrect, because in order to get the proper cancellation, what you need is that this acts not on E but on the co-triad. So again, I was sloppy in this regard. So yeah, when you put in the co-triad, that's when this vanishes, and that makes sense because we are talking about the Gauss constraint. So the Gauss constraint tells us something about the electric field, and well, that is that electric field that we should, the correct one is this triad, the dual of this object. Okay, so the area which corresponds to the area flux. All right, so having cleared these two points, I will continue with the discussion of this thing, actions with boundaries. Are there any other points that if I have overlooked or not done justice to, please let me know. Okay. Anyway, so actions with boundaries, in the presence of boundaries. Now, when we looked at the Palatini action, and we write it down, it looks like this. Why did you require invariance in Netherlands? Well, sir, because I mean, large gauge transformations also are, you have to consider the invariance under both small and large transformations, right? So, I mean, I don't follow your question. I'm not sure how to answer in that. So, Haidar sir, so I'm not sure how to answer the question. So Haidar sir is asking, why do I require invariance under large gauge transformations? And well, because well, I mean, why do we require invariance under small gauge transformations? In QCD, it is not true that large gauge are invariant. Right. So again, I might be making some other mistake here, but it is true in general that the level of the Chern-Simons term is quantized, because when you consider the quantum theory, right, and this goes back to work by Witten on the Jones polynomial and QFT. Okay. Okay. All right. Good. Thank you. So this action with boundaries. So what is the Palatini action? It takes this form. It looks like this. Again, sorry. Blue. E wedge F. Devamalya, I don't know I'll try to let me just try to go over this. All of these are good questions. Let's save them for the discussion at the end, right? So when we do the variation of this, so what is this? This dual. This is the Hodge dual. So we have 1/2 epsilon mu nu alpha beta e nu I e nu j, like this. This would be the dual of the wedge product. Okay. So now when we perform the variation of this with respect to the connection, right? I told you that we use this Palatini identity, according to which the change in the field strength tensor due to a change in the connection can be written as the original field strength tensor plus the gauge covariant derivative with respect to the unmodified unperturbed connection of the perturbation delta A, right? So we use this Palatini identity in to calculate this variation, and the way that works. So we have to perform an integration by parts, right? And what we get is that this thing, we get f, the original f plus this derivative of dA, right? And so our delta S becomes this derivative of delta A, and there's a trace everywhere. Okay, and now we perform an integration by parts. So what we have is that we get a net derivative term, right, which looks like this: E wedge A, and the other term is the part that E wedge. Yeah. So this is the part that gives us the equation of motion. This gives us the equation of motion for the connection, and basically that equation of motion is a statement that your connection annihilates the cotriad. But you also have this boundary term, right? This is the net divergence. So let me just write down. We refer to this object as sigma. Okay, so then our expressions become slightly more manageable. And I get trace of sigma wedge. So now when I perform the variation, right, I get this boundary term, and so I'll call it SP1, which is right. And when I perform, so this can be integrated, and if I have a boundary, this is equivalent to, so I have some manifold M. This is equal to the integral over the boundary of the manifold of sigma wedge del A, again with the trace. No, sir, it is delta A, because when I look at this F, right? The Palatini identity, I get the covariant derivative of del A. So this expression here, I get del A. So it is sigma wedge del A, not sigma wedge del F. All right. So now I think what you're saying, I'll come to that in a second. That comes from the isolated horizon boundary condition, according to which this sigma becomes equal to F, and then F wedge del A becomes the Chern-Simons this thing differential. Okay, so I think maybe that's why there might be the source of the confusion. So this is a boundary term, right? And now in order to have a well-defined variational principle, right, we require boundary terms to vanish, right? I mean, because when you're talking about doing the variation, you keep the connection or whatever your variables are fixed on the boundary, right? So what needs to be done to fix this is that you take your original Palatini action, and so to this action we need to add a counter term, a boundary counter term, and that boundary counter term will just be this something minus k by, I think some, again, the boundary counter term will just be the negative of that variational term. So this is m, this is boundary of m, d cubed x trace of sigma wedge del A. Second. Okay. Let me just double check. Yeah, viewer. Great. Okay. It's sigma wedge A, not del A. Right? Why am I getting that? Okay. Yeah, it should not be del A. It should be sigma wedge A. So 1 second. This should be sigma wedge A, not sigma wedge del A. Right. It should be sigma wedge A. Right. Makes sense. Because we want to take the variation delta S. So when we take the variation delta S with respect to A, in this term, we will get sigma wedge del A. And then that term will cancel out this sigma wedge del A term. Okay. So this is the correct variational principle for a manifold which has boundaries. Okay. Now the question is, what does all of this have to do with black holes, right? So, well, I mean, if we have a black hole, right, we think of it, there is one way to think of the presence of a black hole is that there is an inner boundary to your space-time, right? Just like if you have a cosmological horizon, that's a outer boundary of your space-time. So this is your manifold M, and this is it has some boundary, inner boundary dm. And now one way to make this part vanish is that, so because of the presence of this term, what happens is that the gauge fields on the boundary, they become, rather than just being something, some residual of the bulk diffeomorphism and gauge symmetry, the boundary gauge fields also become dynamic, right? And the way that happens is this is as follows. So when we have this inner boundary, so it's not just any boundary. We identify this as something which is topologically S2 cross R, right? So this is the null surface which forms the horizon of the black hole, right? And S2 are the spatial slices and R is the time parameter. And in terms of the so the way we define this surface is as follows, right? This is a null surface. Now, any null surface in 4 dimensions, we are in 4 dimensions right now. We haven't done the 3+1 split. This is all 4 dimensions. So in 4 dimensions, the way you characterize this horizon, so maybe I'll draw it as a cylinder instead, is that it is a null surface and it has 2 null normals, right? Any null surface has 2 null normals, right? And so we'll take both of them to be future pointing, and one is inward and one goes outward, okay? And this surface we call this surface an isolated horizon, right? And the isolated horizon satisfies certain properties. One of those properties is that it is a trapped surface. So what does that mean? That means the expansion of the outgoing normal, so I'll write that as theta L, the expansion of the outgoing normal is 0, right? So when you consider some space-time in which a black hole is forming, okay, and let's say this is your conformal diagram, and so this is the horizon, right? And you have some matter that falls into the horizon. At some point, the black hole starts forming, right? This horizon surface develops. Now, the horizon itself is something that is very non-local, right? So this is a surface which has topology of S2 cross R. And what we are doing is we are looking at certain spatial sections. So this is a Penrose diagram of a space-time, of an asymptotically flat space-time in which a black hole forms due to collapse. And so this is a horizon. This is a spatial slice sigma. Okay, I don't know what that question means, so I'm going to let that be. And also, it takes us away from the main thrust. So these points, I mean, I don't know if everybody here is familiar with Penrose diagrams. These points are known as scry minus, scry plus, and this is I think scry naught. So this is null infinity, and this is the past null infinity. This is the infinity at the space-like, in the space-like direction. This horizontal line corresponds to null infinity in the future. This horizontal line corresponds to null infinity in the past, right? So this is a conformal compactification of your space-time. And what happens in the conformal compactification is that the causal structure, which means the structure of the path that light follows, remains the same, right? So light is still light. All surfaces which are light-like are represented by diagonal 45-degree lines. So, and all spatial sections, they end at this spatial infinity on one end, right? So if you have any spatial slice, it will always begin somewhere here in the interior and then end at this point. So what is the property of this horizon, right? So when we want to describe a black hole's, like, I mean, we think of it something which is from which light cannot escape, right? And more precisely, so we say that this expansion parameter, right, of this non-normal, the outgoing non-normal, is 0. So this defines a trapped surface. Okay, and the expansion of the ingoing non-normal is negative or 0. And the horizon is defined as the outermost of these. So you have some collection of marginally trapped surfaces, and the horizon is identified as the outermost such surface. Okay. Now what happens is that when you consider these isolated horizon boundary conditions in detail, using this Newman-Penrose tetrad formalism, so these are two of the null tetrads, and then you can define two other null tetrads, MA and MA bar. So together you get 4 null tetrads. So this is called the Newman-Penrose tetrads. So we know what tetrads are now, right? So that's what these are. But the only thing is that these are all null. So this is a null basis, and the reason it's useful to have such a null basis is because, again, you want to understand the causal structure of your space-time. So that's why, you know, having a null tetrad is useful, right? Because null directions are the directions along which light propagates. So in terms of these null tetrads, one can write down all these various curvature invariants, the Weil invariant, and there are a bunch of other Newman-Penrose invariants, some psi's and phi's and all that. Okay, I won't go into all of that. But what happens is that the net conclusion is that for such a surface, you have the following boundary condition. The pullback.
Can you tell me the definition of null tetrad?
Null tetrad. Okay, sure. Null tetrad is basically, these are all null.
I see.
Null means they are all null vectors.
Mm-hmm.
Right? So you can always construct a null tetrad. So for example, let's say you have some tetrad basis, E mu I, right? From this one can always construct a null basis. Right? So more simply, I mean, if you're working with some coordinate system, T, X, Y, Z, right? You can, for instance, go to some coordinates like this, U, V, Y, Z, where U would be something like X plus T and V will be X minus. And so V will represent the outgoing light rays and U will represent the incoming light rays. Right? So if you have this kind of a picture, xt. So if you work in this UV basis, right, you'll have something like this. This will become your, these will be your surfaces of constant V, and these will be your surfaces of constant U. And these are null surfaces, right? According to this, you know, if you put a CT there. And so if you are working in a general, in an arbitrary space-time, right, with some curvature, right, so you can't define the same, you know, what you need is you need to define the basis at each point, and that basis is some set of tetrads. And then from this tetrad basis, one can always construct, by taking linear combinations of the individual vectors, you can construct a null basis in the same way as we are doing here, right? So this we are taking the linear combination of these two vectors in the direction of x and direction of t, and constructing two null vectors uv the same way. We can do it for arbitrary tetrads.
Okay.
And so these are particularly nice for exploring gravitational waves, for instance, because again, gravitational waves propagate along null directions. All right, and one, for instance, you have something called the Wild tensor, right? And the Wild tensor can be written in a very compact way in terms of these null tetrads. Again, I don't remember the exact expression, so if I'm wrong, something like this. Okay. Again, please check. So the Wild tensor measures the part of the, how does one get four of them? Well, you take two of your directions, make a, how does one get four of them? Yeah, that's a good point. Again, let me not go into that. Just take my word for it that you get four of them. Okay. It will again be too much of a diversion for me to go into why we have four of them. All right. So we have this this basis, and right. Thank you, sir. So what happens is that we define these surfaces as trap surfaces, right? Such that the expansion of the outgoing normal is zero, and the expansion of the ingoing normal is positive or zero. So this is what it means to be a trapped surface, right? Is that if you have light rays, so what does it mean that the expansion is zero? That means that the surface cannot grow, right? The surface cannot grow in time, and that is what you expect physically the horizon of a black hole to correspond to, right? Something which, that if there is if there are any null directions on that surface, those null directions cannot go anywhere out. Okay. So yeah, and Adda sir, I think these two vectors might not be null. Okay, so I will not. So it might be two of them are null, and that much I know for sure.
Deepakda.
So when you look at this isolated, yeah.
So what does the bar signify over M?
Complex conjugate.
They're the complex vectors.
Yeah, right. These are complex linear. These are linear combinations of some other vectors, and one is the complex conjugate of the other. For instance, it would be something like, you know, M is equal to Y plus IZ, and M is equal to Y minus IZ. And that's how you, okay, so that's how you get the four null directions. So Haridas sir was asking, how do you get four null directions? You have to take these complex linear combinations. Okay. Now, right. So now what happens is, now what happens is that you have this surface, right, and you have the bulk, these bulk quantities, right, E mu j, and then your this thing, which is the, so this is also mu nu ij, which is the dual of E wedge E, right? And so these two can be pulled back to the horizon, right? You can ask, what is the restriction of these objects to the horizon? And so on the horizon, on this isolated horizon, we can define a triad basis. Okay, so now what we are doing is this isolated horizon, right? It's actually some it's some null surface which is embedded in inner boundary of a four-dimensional space-time, right? So we consider three-dimensional foliations of our space-time. So this is a single foliation at a single time, at a constant time, and this foliation will intersect your horizon at some boundary, and this boundary is your trap surface, and at this boundary we will define a set of triad fields. So basically this has a topology of a two-sphere, right? And on this we will define a triad such that two of the triad vectors are tangent to the surface and one is normal to the surface. Okay, so nicer way to, I don't know. So we have one vector which is normal to the surface and two vectors which are tangent to the surface, right? So it's just like you take a ball and you put if you put spherical coordinates and you consider the radial vector field and the angular vector fields, right, r, theta, and phi, you can just think in terms of those objects, right? So the radial vector field will be pointing, will be normal to the surface, and the angular vector fields will be tangential to the surface. So you can just think of these tangential vector fields as corresponding to those radial vector fields. All right. So now what happens? And similarly, you have some gauge connection in the bulk. This gauge connection can also be restricted to the boundary, right? It can be pulled back to the boundary. And when you pull back this gauge connection to the boundary, what happens is, right? So in the full four-dimensional bulk, it's some a mu I. This is in the full four-dimensional bulk. When we restrict to the spatial foliation, right, we get some three-dimensional SU2 connection or SO3 connection, depending on your flavor, right? These are now three-dimensional indices. And then this object can be further restricted to this horizon surface. Okay, so when you restrict, then again you can define the curvature of this connection. So on the horizon surface, we have this quantity, which is the pullback of the three-dimensional bulk curvature to the horizon surface. And you have another quantity which is formed by these triad fields. So that is this ABI, which can be written as epsilon ijk EAJ EBK, right? So this is defined on the horizon surface. Okay, so again, we'll write it as some pullback of sigma to the surface. So it turns out that these isolated horizons, they can be shown to satisfy a certain boundary condition, and that boundary condition is as follows. So let me again be a little bit careful, not write anything. Right, so this is what the boundary condition looks like. Minus 2 pi by A naught, where this A naught is the area of the horizon of the spatial slice, right? And then you get some factor of 8 pi G gamma, and then you have something which looks like this. So, and there's also an Ri. I will explain what this Ri is in a second. And times Ri. Okay. So this Ri is a vector field that is defined on the surface, and it gauge fixes your connection. So this gauge fixes, this is like a gauge fixing. It's sort of like when you make the choice of this triad, right? You are reducing, you're fixing your gauge, because you remember that your theory has local SU2 gauge invariance, and that SU2 gauge invariance is corresponds to the fact that your triads can be locally rotated, right, under SU2 transformations. So if I make the choice of a triad of this form at each point on the surface, then what I'm doing is I'm fixing the gauge, right? And the way I fix it is by making a choice of a vector field on the horizon. And so this vector field contracted with the curvature tensor on the one hand is equal to the contraction of the vector field with the with this triad. So I'll write this as sigma AB. So I'll give a more physical interpretation of this constraint. Okay, so this is called the isolated horizon boundary condition, and as such it might not look very transparent, but it has a physical interpretation which hopefully is a little bit more enlightening. And so what is that physical interpretation? It is that right. What is this, right? This is the flux of the connection, this thing. So if you look at, you have some, if you consider some, again, that picture in terms of loops and fluxes, you have some loop. Around that loop, you have some connection, right? And if you go around the loop, you get some non-trivial holonomy if there is a flux through the loop, right? So you imagine that there is a magnetic field. This is your magnetic field, and it has a certain flux through your surface, right? So you would write your flux as something like this, right? This is your usual definition of flux, dotted with some normal integrated over your d2x. Okay, and this is our electric field, right? So so the statement of this statement is sort of like saying that the magnetic field is proportional to the electric field. In terms of Yang-Mills variables. Okay, Yang-Mills phase space. So in Yang-Mills theory or Maxwell theory, for simplicity, right? You have an electric field and a magnetic field, which correspond respectively to the you have a curvature tensor, and this is your electric field, and then you have your magnetic field, which is this the spatial part of this tensor, right? So if you impose this, imposing this condition is equivalent to saying that your magnetic field is some proportional to your electric field. And in Yang-Mills, this condition is often written in terms of these variables as E plus IB and E minus IB. These variables are often used when talking about the Yang-Mills. So these correspond to the self-dual. So curvatures which have this property are called self-dual. So if this curvature satisfies this property, it is, so what is the meaning of self-dual? It means that if I take the dual of this curvature, I get the same thing. So it can be plus or minus. So this means it is self slash anti-self dual, right? So this condition, right, exactly. So this condition on the boundary, it reduces to saying that the field strength tensor is self-dual. So the isolated horizon boundary condition is equivalent to saying that the boundary curvature, and only the boundary curvature, not the bulk, is self-dual. Okay. Now again, this doesn't necessarily doesn't necessarily give you much more physical insight, I suppose, but still it's better than nothing, right? Okay. So anyway, once we have this boundary condition, then something nice happens. Now we go back to the Palatini action in the presence of a boundary. Okay. Now you remember that this is what happens. This is your bulk Palatini action, your four-dimensional action, and this is your boundary counter term which you have to add in order to get a well-defined variational principle, right? And this is defined on the inner boundary, right? But now what we have is we have this isolated horizon boundary condition, which tells us that on the horizon, this sigma is proportional to the field strength F. Okay. So isolated horizon boundary condition is saying that on the horizon, your sigma is proportional to your to your field strength, the pullback of your tensor, curvature tensor to the boundary. Okay. Now what is the effect of this? The effect is that when you look at this curvature of this variation of the Palatini action once again, right? So again, let me I'm just looking up just to be, so I don't again say anything too incorrect. And in case you are wondering, the references, there are some very nice references. I'll tell you what they are. Okay. Right. So when you look at this variation, what would happen to your in your Palatini term? On your boundary, you would get so you would get something which looks like sigma wedge del A, right? If you don't have a boundary counter term, this is what you would get, right? So then you would add a boundary counter term. But let's say you don't add the boundary counter term. Then this is the variation on the boundary. Okay. But now we are saying that our boundary, and this is a 2+1 dimensional surface, satisfies this isolated horizon boundary condition. And the isolated horizon boundary condition is very general. It applies to both charged and uncharged black holes. And the black hole space-time also does not need to be static. So, I mean, as long as you have a horizon, it applies. It's not only to Schwarzschild space-time. So this isolated horizon boundary condition implies that your action, this boundary term, can be written as your F wedge A d cubed x, right? Because that is what the boundary condition is. It says that F is proportional to your the sigma, where sigma is your when this sigma, let me just is called a bivector, right? So in 4 dimensions, if you take the dual of a 2 form, you get another 2 form, right? And this is a 2 form. So this is now your surface term looks like this. Okay, it looks like F wedge dA. Okay, and F wedge dA and again, as a trace, I should not forget that trace. F wedge dA. One second, something in the chat. Demolia is saying something in Yammel's theory, self-dual solutions can lead to finite energy configurations. Yeah, I mean, self-dual solutions have all sorts of nice properties. But the thing is that here, again, to emphasize, the solution is self-dual only on the horizon, not in the bulk, not everywhere. Okay. So whenever you have this kind of a structure, this can be written as the total differential of a Chern-Simons Lagrangian, right? So what is the Chern-Simons Lagrangian? Again, trace of A wedge dA plus 2/3 A wedge A wedge A, right? And if you calculate the differential of this, again we have seen that this differential is precisely F wedge dA. Okay. So to recap, when you have in your Palatini action, you perform a variation of this Palatini action, and you get this boundary term. Then you say that you have your inner boundaries, and these inner boundaries satisfy the isolated horizon boundary condition. Since they satisfy the isolated horizon boundary condition, the boundary term can be written as this object, and this object can be written as the total differential of the Chern-Simons Lagrangian. And where is this Chern-Simons Lagrangian? It is defined on the boundary. Okay, so finally what we can say is we can define our action in the following way. Our complete action for gravity with a boundary with an isolated horizon. It looks something like this. You have M, that's your manifold, your four-dimensional space-time. So then you integrate this thing and over the four-dimensional manifold. Then you have your boundary of the four-dimensional manifold. Over that, you have to put this counter term, sigma wedge A P cubed X. And then finally, to take into account the isolated horizon boundary condition, you have to put in another term, which looks like this. The delta is the isolated horizon, which looks like this. Trace of A wedge dA plus 2/3 A wedge A wedge A. So the point is that so this is S delta C. Okay, and the point is that if you have these isolated horizon boundary conditions, that is equivalent to saying that you have a Chern-Simons theory for the pullback of the bulk gauge field living on your boundary. So again, well, this term I don't. I mean, it's I get confused. This term I'm not sure like how it stays in the picture. I thought it should go away, but it's there. Anyway, the net result is that we get a Chern-Simons theory living on the boundary. So what we have in the end is the following. In Palatini gravity, right? And whether we use Ashtika variables, all right. So with Ashtika variables, in the bulk, we have the Palatini action. And in the presence of an isolated horizon, we have a non-abelian Chern-Simons theory living on the horizon. And maybe this answers Takato's question. Takato had asked this question, right? That that work over the past several years has people have looked at the soft modes, which correspond to the BMS super translations of the horizon, and shown that they give you the entropy. So Takato had asked whether you have something similar in the LQG case, and so again, I've looked at this. The BMS formalism is very dense, and so I've not gone into it in great detail. Hi, bolna hai. 1 second, please just say hi to the little physicist. Okay, hi बोल दिया? हाँ, ठीक है? Flying kiss दे दो. Okay, he's given a flying kiss. That is very rare. Okay. See, it's like you have to feed the monster. You have to satisfy its craving. Okay, so you have a non-abelian Chern-Simons theory living on the horizon, right? And this is also what happens, for instance, like if you consider some gauge theory living on a disk, right? So on some two-dimensional surface, and you consider a hole on this two-dimensional surface, right? And you have, let's say, Chern-Simons defined in the two-dimensional bulk. Then what happens is that gauge transformations of this bulk theory do not vanish. The variation of this action does not vanish on the boundary, right? And so this induces this one plus one dimensional theory on the boundary, which is called I think the Wess-Zumino-Witten theory, right? So you sort of have this dimensional ladder. Okay, you have in 3 plus 1 dimensions, you have this gravity. In the presence of isolated horizons, in 2 plus 1 dimensions, you get this Chern-Simons. And then one can further imagine that your horizon has punctures, right? And that actually does turn out to be the case. So if you have punctures on the horizon, then you get 1 plus 1 dimensional WZW theory. And so when you calculate the entropy of your surface, of your horizon, right? So now how do you relate all this to the entropy? Well, when you look at this isolated horizon boundary condition, so what one does is we impose this boundary condition on the state space, which are the spin networks. And what this condition does on the state space, so you have some spin network, some graph, and it is, we don't care about what's happening in the interior. It doesn't matter. All that matters is that the boundary state is being fixed by the choice of J labels that we have given to the edges which pierce the boundary, right? And So this becomes, so in the quantum picture, this becomes the Chern-Simons theory with on a Riemann surface with some number of punctures, with n punctures. And what is the area of this surface? Again, we define the area as I explained the other day, that we look at the area operator and we say that the area is this object. LP is the Planck length, so this is LP squared. So it's the sum of the areas associated with each puncture, right? And the Hilbert space is the space of right. Haridas sir is asking this question, and it's a very nice question. It's that, are these punctures to be understood as physical punctures on the isolated horizon, right? And yeah, I believe they are. I believe that is how one should understand them. Because you know, I mean, this is what the picture tells us, is that your horizon is made up of patches, quanta of area, which are all linked together, right? So there is a tiling or a tessellation of your horizon, and essentially when you're counting the black hole entropy, what you're doing is you're counting the number of ways in which you can tile a surface, right? Or the number of ways in which you can triangulate a surface. So if you think of each of these punctures as associated with a single tile, right? Then so each puncture is a physical degree of freedom. Yeah. So I do view these as physical punctures on the isolated horizon surface. Though, you know, some people might disagree with that and say that no, this is just a mathematical tool, you know. But I mean, if you look at Maxwell's equations, you get the wave equation, and some people used to think that the electromagnetic waves are simply a mathematical tool, or but then, you know, until somebody measured the transmission of radiation from one point to another through a transmission of energy. So and triangulations are not the same as punctures taken for Riemann surfaces. Right, triangulations are not the same as punctures, but I'm just giving an analogy that you know, counting the configuration of punctures is akin to counting the triangulations of a surface. Right. In fact, one can show that if you do count the triangulations of a two-sphere, and this is work done by Thurston, you reproduce exactly the Bekenstein-Hawking entropy. Right. So there is a paper by Thurston. Thurston is famous for the geometrization conjecture in mathematics. Right. And so he has these very beautiful papers, right, where he counts the number of ways in which you can triangulate a two-sphere, and he relates that to the volume of some hyperbolic manifold and etc. And you know, he gets this number of ways in which you can triangulate goes as exponential of the area. So, okay, so coming back to this picture, now we have the Hilbert space, the corresponding Hilbert space, and we want to calculate the entropy of this of the state, right? And the entropy would be associated with the dimension of the Hilbert space, right? And the dimension of the Hilbert space can be calculated explicitly, and so let me again not be too glib about this. Yeah, let me look at the reference. So I'll also give a you know, this thing, a bunch of references that that you can look up if you're interested, which shows all of these results. And so let's see. Okay. This gives us this black hole is proportional to the area. Okay. Now let me give you some references so that you can investigate this. Haridas sir has left, but he has said that today's lecture was very inspiring. and I don't know. I hope that, well, if inspiring, that's a very, very strong comment. I don't know. I hope that, you know, inspiration is, I don't know if that's what I'm conveying. So let me give you some references so to the literature. This isolated horizon phase space was first discussed in the mid to late 90s, mid to late 90s, in papers by Astiker, Baez, Korichi, and Krasnov. And thank you, Dev Malya. That's a good, you know, it means a lot coming from you. So the isolated horizon phase space in the mid to late 90s was discussed by these people, right? So they show that they explicitly, in terms of, you know, there's all this symplectic structure and whatnot. Then following their work, Romesh Kaul and Parthasarthi Majumdar. So Devamalya and Preetham, you might have heard of these people. I think Romesh sir has just retired, and I don't know about Majumdar. So Kaul and Majumdar, they showed, right, that immediately it follows you can use this Cardy formula to calculate the dimension of the Hilbert space of Chern-Simons theory with n punctures. And they showed that this Chern-Simons formulation immediately leads you to this black hole Bekenstein-Hawking entropy. And well, with some gamma factor, which is gamma is this image parameter. And then furthermore, they showed that there is also a logarithmic correction to the black hole entropy. So I'll just write it something like this, minus log A. This logarithmic correction also arises from this Chern-Simons description. And now so it was around 10 years ago or 11 years ago now, so around 2010 or so, when there was further, so there was a lot of work in between, okay? There was a lot of work in explicitly calculating this entropy, numerical simulations, enumerating all the black hole microstates and so on and so forth, then work in terms of using generating functions to calculate this entropy. And of course, before this, I should mention that around the same time, sometime 1996, I think, Rovelli, and then separately Rovelli and Krasnov. Right. So Rovelli did a very simple sort of calculation, counting of this without resorting to any Chern-Simons theory, counting of black hole punctures, and showed that you get the Bekenstein-Hawking entropy, right? And then in between there was, like I said, there were lots of work by lots of other people, but then Engel Perez, Nui, and Pranzetti, these people, in a series of nice papers, they filled in a lot of gaps. So there had been gaps in Ashtikar's work, okay, and you know, I mean, so these guys filled in all those gaps and showed that, well, you do get SU2 Chern-Simons theory on the horizon. Okay, so this was the yeah, it made everything completely, you know, solid. And finally in right, and then in 2012 there is a very nice review paper by Romesh Kaul on black hole entropy. So he summarizes all of these results, and he talks about the different methods that are used for calculating black hole entropy. So I'll leave it here for today, and yeah, and so we have, I mean, I can have 2 more sessions, I guess, and in the next 2 sessions I can talk about spin forms, which are 4-dimensional histories of space-time, and this is also, you can call it covariant LQG, right? So when we have been talking about this LQG, where we are fixing a foliation, and so the covariance is lost, right? So how do you restore that covariance? How do you restore that 4-dimensional space-time structure? So that is where this spin form formalism comes in. And then in the lecture after that, I think I would want to talk about something called group field theory, and then tensor networks, and the relationship between all of the ongoing approaches. And yeah, I will provide the link of Kaul's paper in Zulek also. Okay, so today was number 11. In number 12 and number 13, this is what I'll talk about. Okay. All right. So questions?
Oh, well, I have a question.
Yes.
So in today's lecture, the isolated horizon boundary condition
Your voice is
derived.
Your voice is.
Can you hear me?
Now I can. Now I can. Yes.
Okay. So in today's lecture, the isolated horizon boundary condition is naturally well derived, but I thought the boundary condition is something imposed by hand. So
No. It is, well, I mean, it is imposed in the sense that, we have some physical requirement that, I mean, when we say that there is a horizon, it should have some physical properties, right? I mean, otherwise, like you said in the previous lecture, any surface can be a horizon, or any surface you can do this entropy, this state counting for, right? So you need to have some identification, some way to identify, well, which surface is the horizon. And the identification is in terms of these expansion of null vectors, right? So this definition in terms of trapped and marginally trapped surfaces. So basically, you say that a black hole starts forming when these trapped surfaces start appearing, right? Until you have a trapped surface, any light like geodesics can escape to infinity. But the moment a trapped surface forms, and such that the expansion of the outgoing null rays is 0, well, that you can think of that as a light, as the surface as a light front, right? And that light front cannot go anywhere; it's not expanding, right? So if you have a flash of light, right, you get this expanding light front. So if this has a 0 expansion, that means that something is keeping it, something is trapping that light in. So as soon as these trapped surfaces form, you say that that is what, and the outermost trapped surface is what you identify as your horizon.
Is a trapped horizon different from event horizon?
Right. So an event horizon is a global and a non-local object. And event horizon, so as I was showing in this diagram, an event horizon, which is this line, this line over here, right? The diagonal line. That is your event horizon, and it's a non-local object. And the thing about this event horizon is that it is also a tautological object. Because if there is a black hole collapse occurring somewhere far away from me, an event horizon could be forming in the middle of this room without me knowing it, right? So you need to know the full global history of your space-time to say what the event horizon is. On the other hand, the isolated horizon is just this part. This is the isolated horizon. So isolated horizons correspond to spatial sections of your full event horizon.
I see.
Right. And by the way, in this Penrose diagram, right, when you perform this conformal compactification, you have a time direction, and you have a radial direction, which is the spatial direction, and then you have 2 more directions, right? You have 4-dimensional space-time. So each point in this diagram corresponds to a 2-sphere, S2. So it's like when you take when you look at, for example, the line element minus dt square plus dr square plus r square d omega square. So each point is like that d omega, right? So this is the isolated horizon right here. Or at least what if it satisfies the right properties, that's what we would. And yeah, so in a real sense, this is a physical surface. This is a physical surface in the real sense, and it's, for example, it's what this Event Horizon Telescope is seeing, right? I mean, the Event Horizon Telescope is seeing a surface, right? Once it has better resolution, as it probably will in a couple of years, right? We will see a very clearly defined surface. Right now, it's a little bit, it's quite fuzzy. You have a blob of light, and then you have a bunch of darkness in between, but the boundary is fuzzy. Once the resolution improves with more data coming in, we will see a clear, the surface will become clear. The boundary will become quite clear, right? And that boundary is a physical surface. It's the horizon.
Well, I have a related question. So,
Yes.
well, I think you said this isolated horizon is not well defined for rotating black hole. But
right. So then, right.
why is,
so then you have this notion of dynamical horizons also.
Mhm.
So again, that's, you know, a whole set of other, a whole different.
well, my question is, in case
Yeah.
of rotating black hole, we
Yeah.
have an ergosphere and we have outer horizon and inner horizon. And
Right.
we identify the intersection of a costed surface and the outer horizon to be this isolated horizons. Then I thought there is no problem, but
Okay. No, I mean, again, I don't know. I mean, that statement might be wrong. So I'm not going to. What is you saying, that you identify what intersection?
the intersection of costed surface, special slide, I mean, one,
Cauchy surface, right? And
yeah, and the event horizon, the outer horizon.
right. No, I mean, it's the same thing here also, right? This is a Cauchy surface.
Yeah.
This is the horizon, and
So
so
just,
yeah.
yeah, it isn't, does it can be applied to the rotating black hole?
Yeah, I mean, it can, but there are some issues having to do with what we call the closure constraint. So I haven't talked about this closure constraint. So when you have these spin labels, okay, so I'll tell you what this closure constraint is and how it can be used to talk about rotating horizons. So when you have these spin labels, right, the spin label doesn't specify the state, right? So if you imagine that there is an actual physical spin living on the boundary, then it can have 2j plus 1 states, right? The Hilbert space of each spin is 2j plus 1 dimensional, right? So for instance, if j is 1/2, your spin can be up or down, right? So there's a magnetic quantum number associated with each puncture. So each puncture we should write as j comma m, and so on. And now the requirement of having a total. So what is the interpretation of these m's? If you take the sum of all of the m's, right, and this is 0, this means that your surface is non-rotating. So the sum of all your m magnetic quantum numbers determines the total rotation of your surface. Another way to picture it is that again, you think of this is your two-dimensional surface. Let's say I put a puncture here, okay, and then I can think of m is equal to plus half, for instance, as corresponding to rotation in the right-handed sense, and m is equal to minus half as rotation in the opposite sense, right? So now if I have 4 punctures, let's say, and each puncture has a rotation associated with it, right? Then when I look at the rotation of all 4 punctures, right, I will get a net rotation. So if I take some line and I enclose these 4 punctures, right, and I calculate the holonomy of the connection around this closed curve, I'll get something non-zero, right? So, and if so it's like saying that you have a spin up, a spin up, a spin up, right? So you have spin up, spin up, spin up, and spin up. Something like this. This corresponds to a rotating horizon. But there's a problem with this kind of a state. So I would identify a state of this kind. Let's say I write it like this, okay, or this, right? Both of these have a net non-zero m magnetic quantum number, right? So m is not equal to 0. M, which is the sum of all the magnetic quantum numbers, is not 0 for this psi, right? Now, what the problem is that if I look at this kind of a state in this spin network picture, these states are not gauge invariant. These states are not gauge invariant. So the Gauss constraint is not satisfied by these states. But I think that, again, that is not a problem, because if you have a rotating, if you have rotation, then I think the Gauss constraint will be violated. So, but again, I don't know of a clear and proper way to state that. So if you look at the gauge invariant states in this spin network picture, actually I should have talked about that. Maybe I'll do that in the next lecture. I didn't really talk about this intertwiner phase space. I didn't talk about the volume degrees of freedom, volume operator. So I'll talk about the volume operator in the next lecture. And so this volume operator, so you can associate a volume operator with these vertices, with these intertwiners, right? And you can think of a black hole as an intertwiner. If it's a macroscopic black hole, you can think of it as a giant intertwiner, where you have trillions of edges coming in to a single huge giant vertex, composite vertex. And when you look at these intertwiner degrees of freedom, then these are for gauge invariance, which is basically the Gauss constraint. This requires us to impose this closure constraint on the states, that the sum of the magnetic quantum numbers has to be 0. And this closure constraint is equivalent to saying that, for instance, that if you have a bunch of triangles, if you have 4 triangles, and you ask whether those triangles can be glued together to form a tetrahedron without leaving any gaps, right? Or right. So if you have 4 normals, if you have these phase normals n1, n2, n3, and n4, then, for instance, a tetrahedron satisfies this condition, right? I is equal to 1 to 4, and this is true for any polyhedron. And this is equivalent to this closure constraint in terms of these magnetic quantum numbers. So, so the thing is that if you say that this m is not equal to 0, right? This implies that your intertwiner, your vertex, is not is not gauge invariant, right? With respect to gauge transformations acting at that vertex. But this is what I would physically think of as rotating, as a rotating horizon or a rotating intertwiner, right? Now, I mean, it seems to me that this actually makes sense, that if you have rotation, then gauge invariance, it will not be gauge invariant. But again, I don't have a I just have a gut feeling to support it. I don't have any mathematical argument to say why that should be the case. But it seems that it should, there's no problem with it, that yeah, we do expect violation of gauge invariance. I just think of a tetrahedron, and I think of it, a tetrahedron spinning. And if it spins, like somehow the flaps, the leaves will open up. That sort of picture comes to mind. I mean, it sounds very childish. I don't know, but yeah, that's a sort of
Okay.
Visually, I like to think that way. So, people have looked at these. There's Hanno Salman. He has looked at it at horizons with rotation. But I looked at his paper and I couldn't really make sense. I mean, it didn't. I mean, I didn't like see some simple physical picture. And I'm very fond of simple physical pictures. I want to condense everything down into a cartoon, into a Calvin and Hobbes. I don't know if you're familiar with Calvin and Hobbes, but I think all of physics should be you should be able to express it as a Calvin and Hobbes cartoon. So, and yeah, I'll leave it at that. So yeah, thanks everybody for coming, or all four of you, and well, now it's only three of you because I think Mustafa left. So we have Devadarshini and Takato and Devamalya. And I think Preetam also. Preetam is also there. Preetam is also there. So four of you. All right. So I think that today's lecture went well compared to some of the other ones.